Hello.
Hello.
Hey, how's it going?
Good. How about you?
Doing well. Thank you for asking. Do you have the homework? I know there are only two problems that I assigned and then three if you count the challenge. Were you able to get those done?
Yeah, I believe so.
All right. So I was hoping that you could just maybe do them on the screen right now. Maybe just
All
kind
right. Sure.
very nice.
All right. That's what I got for those three questions.
All right. So the first two look good. Let's talk about this last one. So this does come into play at some point in the things we've learned in this class. We know that the derivative of tangent is secant squared, but what are we doing here when we have this symbol here? We know that's the integral symbol. How do we integrate a function algebraically? What is the process like?
Um, for me, it's just it's considering what's at whatever is like behind the dx as the derived function, and you have to sort of undo that derivative to find the original function.
Yep, exactly. In other words, we want to find the antiderivative. So
The antiderivative. Yeah. Sorry.
no problem. So you found the derivative of tangent, that is secant squared, but how do we find the antiderivative of tangent? That's why this is a challenge problem. It's pretty tricky. I want you to think about a few possible strategies we might be able to use to find the antiderivative of tangent.
Oh, I see.
Here, let me clear away some of the space. I'm going to move this up. And the derivative of tangent is secant squared, but we want to find the antiderivative. So do you have any ideas about how we might do that?
Well, I don't know. For I don't know. I applied the same process as I did like for the second one, the antiderivative of cosine x. I just oh, I see what I did here. Yeah, I see why that was a challenge one now. I knew it was too easy.
Yeah.
Um, I hmm,
So I want
well,
you
we'd have to find a function that when you take the derivative of it, it's equal to tangent
yeah,
tan x.
exactly.
But um hmm.
So think about that for a few minutes. I'm going to put the recording on pause while you think about everything we've done in this class. Think about what strategies might be useful in a situation like this one. All right, let's see what you got.
So I was thinking about it, and I think that the only way that you could get tan of x as the derived function, I think the antiderivative is it's a natural log function where the function of the argument of the natural log is negative cosine of x.
How'd you get that answer?
Well, I know that tan of x is well, I know that tangent of whatever of any argument is sine over cosine. So then I was just thinking, and I was looking through my notes, and I remembered the natural log property where if you have like an actual function as the argument, it just becomes the derivative of the function over the function. And so then I was thinking, well, since tan can also be described as a quotient of the other two main trigonometric, uh, uh, what are those called? Identities are not identities, just sine over cosine. I figured it could be like the original function would be a natural log function, and it could just be like I would say negative cosine, because when you derive that, you would have the derivative of negative cosine uh in the numerator, and then in the denominator negative cosine x. But we also know that negative cosine x is equal to cosine x, I think. So where is it? That's the part that I'm not entirely sure of. I forgot the negative rules for the trig functions.
Oh no, that's brilliant though. I don't think anyone in any of my classes ever got this on the first try. You're the very first one, so congratulations. That's
Wait,
brilliant.
is that it?
You're almost there. So I
Almost.
completely
Okay.
agree that we want to write it in terms of it's going to be sine over cosine. And then you're right. We have to use that logarithm rule from derivatives to help us here. And to make it formal, we're going to formalize this by using u substitution. And I know we didn't really talk about that much. We're going to be talking about u sub a lot more today. So we're going to be
Okay.
doing u substitution in this one. So do you remember in which cases we want to use u substitution? Do you remember which cases in which it's helpful?
I think it was just when your argument of the function is not just x, when it's anything other than just x,
Yeah,
where
not only that, but if we have the derivative of the argument somewhere in the function itself, it's the reverse of the chain rule for derivatives. You can think of it as the chain rule for
yeah,
antiderivatives.
yeah.
So we can never have the derivative of a function be on the bottom. It always has to be on top. So if the top is the derivative, what appears on the bottom has to be the function itself. So we always call that u. So we have u is going to be cosine of x, and then du, derivative of cosine with respect to x, is negative sine of x. And then we're going to multiply both sides by dx, because we always want dx to be part of what we have in the function itself. Our goal is to make what we have match this part as much as possible. We want to make it match whatever is in this box. So we already have the sign, we're missing the dx. So I'm going to multiply both sides of this differential equation, we call it, by dx. So that means the dx on the left goes away completely. And then what I also want to do is I want to multiply both sides by, no, actually, I think I want to leave the negative there. So now I want you to help me out with this next part. I want you to rewrite the integral, but replace dx with all of this stuff and replace u, or replace cosine of x with u. Or hang on a second, sorry. Yeah, I meant to say, no, I had it right the first time. We want to replace actually all of this stuff with du, and then replace this with u, and then see if you can solve it from there.
Why would we do that though? Why would the numerator become du? Because it's the derivative of u. Is that it?
Exactly. And the reason why we have to do that is because then we can use the natural log rule. We can't use the natural log rule the way it is right now. But if we have this become, this would be negative du over u. Now this is going to be, it looks a lot more like this. Do you agree that it looks a lot more like this now? 1 over x dx kind of looks like what we have here.
I don't see why it would. Why? Where did the 1 over x come from?
Oh, this is just the antiderivative for the derivative for natural log. So we have to put this
Oh, okay.
1
Yeah.
over u du form so that we can apply the natural log rules, because we know that the antiderivative of 1 over u is natural log of u. So that's why we even bother replacing all of this on the top with negative du, and replace all of this on the bottom with u, because then we can take the antiderivative using the natural log rules that we learned last time.
Mm-hmm. Okay.
So see if you can carry this out to the end for us. So you said you're okay with doing a 3-hour class today, right?
Mm-hmm.
So would it be all right to do like a 1-hour intermission from 3:30 to 4:30 and then pick up again at 4:30?
And then 4:30 would go to 6:30.
4:30 would go 5:30. We're going to do 1:30 to 3:30. So that's 2 hours. And then we're going to do another hour of 4:30 to 5:30.
Oh, an hour later. Okay. Yeah, sure.
Cool. I'm happy to hear that. Most people would just say, no, that sounds like the worst thing in the world. I don't want to do any more math than I absolutely have to. So your attitude's pretty refreshing. I don't get that a lot. It's really nice.
Well, I really like integrals. I don't know. Just so far, my mom said that they're gonna get to where I won't like them, but
They're
I
fun.
think yeah, I think they're a lot better than derivatives, if you ask me.
Absolutely. Derivatives are just tedious. They're mechanical. You can take the derivative of anything, but they're not fun. Integrals, you have to step back for a few minutes and take a look at what you have and be really strategic about what you want to do.
Yeah,
That's why I like it.
that's
It's like
why
a
I like
puzzle.
it. Yeah, it's like thinking backwards pretty much.
Exactly. Reverse engineering a solution. So
Yeah.
if you ever want to study engineering, you're going to be using this a lot.
Mm-hmm.
So
Okay.
we're almost there. We still have that minus sign out front. So you can either leave it like this, or what you could do is you can use one of those log rules. You can apply the -1 to the argument right
Well,
here.
why would we leave the negative? Because the derivative of cosine is negative sine. So when you take the derivative of natural log of cosine x plus c, you would get what we have in the integral, right?
Oh, you have, this would be, oh, hang on a second. So this would be negative integral du over u. And then we have negative natural log of u, and u is cosine. So you have to have a negative out front only because there's a negative right here. And we did that one rule for integrals that tell us that whenever we have a constant, we can always move the constant right out front.
And
So
so we want to do that every time.
yeah, because otherwise it doesn't really go anywhere. It kind of just disappears without a trace. We always have to make sure we're keeping track of our negative signs, because
Well, but then how would that equal the natural log of cosine x?
well, in its current state, it can't. In this state, it cannot. But if we move this out front, if we move this negative sign out front, make this positive, now we can only focus on what's in here. We're going to ignore the negative for now.
Well, I know, but the negative is a part of the right, because when you take the derivative of cosine and then it goes on the numerator, that's gonna be negative sine x, and then you put cosine on on the denominator. So why would we move the negative out if it's a part of like helping us find the original function?
How do I want to explain this? I'm trying to think about the best way to explain this. Give me a quick second. So I feel like I kind of want to just start over on a particular step so we can just go through this together and I'll be able to explain every part of it and explain why things are the way they are. So
Okay.
we're going to leave off right here. We used that trig identity. We used the quotient identity to write it as sine over cosine. So we have to do it. We have to do that in order to use u substitution. So we have u is going to be cosine of x. And then the derivative of cosine is negative sine. So we have negative du equals sine of x dx. So now we're going to substitute everything in. So sine of x dx is the same as negative du. And then cosine of x is the same as u. So we have a negative out front. We want to move the negative out front just like we would with any other constant. It would be no different if we had something like this. If we had 2 du, we would want to move the 2 out front. In the same way we want to do that to the negative 1. So then from there, we want to take the antiderivative. So what is the antiderivative of 1 over u?
Natural log of u.
Yep, exactly. And the negative's still there. So we have negative natural log of u, and u is cosine of x. And then we have our constant of integration, and we're done. And the nice thing about this is that you can take the derivative of this expression and see if we get the original. So I invite you to go ahead and take the derivative of y and see if we get tangent of x as our final answer.
Okay. It did.
So this part checks out. This is correct.
Yeah.
Cool. But then we want to take it even a step further. I mean, we don't have to, but for the purpose of completion, it's a good idea to know how to do this next part. So there is a special law of logarithms that tells us whenever we have something like this, we can write it like this, where u can be any argument. So we have a negative 1 out front. Another way we could express that would be as natural log of cosine to the negative 1 power. And then we get, this would be 1 over cosine to secant. So we could also write this as natural log of secant of x plus c.
What's this right here?
Oh, that is a really horrible, that's my really terrible.
Oh my gosh, I'm so sorry. Yeah, no, I see it now. I'm dumb.
No, it's my fault. My handwriting is dreadful. All right.
All right, I'm gonna write some of this down.
Cool. No problem. Take your time. Have you ever seen a movie called Stand and Deliver?
Stand and deliver? No.
I think we should watch it one day. I think like we should have like a class movie night. I've been wanting to do that like ever since I started teaching. I don't know how it would work. I think there could be like a way I could like share the movie over Zoom. It's a
Yeah, I
math
think you would have to share your screen, but that would work.
it's a math movie. It's pretty cool. It's about
Okay.
a bunch of kids living in a really poor part of Los Angeles. A lot of them don't even have a glimmer of hope of going to college. And then this teacher comes and he gets them interested in math, and they all end up taking calculus in senior year of high school, which is unbelievable. It's something that they never thought would happen. And I just think it's a pretty cool movie. It inspires me as a teacher to reach as many people as possible.
Okay. Yeah, I'm definitely. It sounds like a good movie.
It is pretty good.
So I have a quick question. This part right here, the negative du is equal to sine x of dx. Um, so the negative in front of the du comes from the fact that when we take the derivative of u, it's negative sine x, right? And
Exactly.
then, but rather than have it on the right side of the equation, we move it to the left.
Exactly. We had this originally, and then I just did this. Yep.
Either way, though, it technically it wouldn't matter where you have the negative sign, though, because in the end, you would still end up moving it outside of the integral, wouldn't you?
Yep. Exactly.
If you were to just substitute du. Okay. So when we apply u substitution, we always choose our u, but after that, you actually take the derivative of u rather than just take the numerator.
Well, it won't always work that way. You have to be really strategic in that you can only use u sub when you have not only a function, but you have the derivative of that very same function somewhere in the integral. So this one works really well because we have cosine, and we know that the derivative of cosine is negative sine. So we have that in some form. So that's a big indication that u sub would work really nicely for us. But it won't always be like that.
In this case, why would we consider sine of x close enough to be the derivative of cosine x if it's
Because we can do
missing?
it's because we can do a quick modification. If we have something like this, it's really easy to manipulate and make this positive cosine and negative du. Whenever you have a
Okay.
constant like that, it would be the same thing if we had something a little bit different. Here, I want to show you a related example real quick. What if we had cosine of 2x? And then I'm going to need more space. So cosine of 2x, the antiderivative of that is going to be, sorry, I keep saying anti. I meant to say the derivative of that is negative 2 times sine of 2x. So then we have to take care of this negative 2 there. We're going to have to divide both sides by negative 2. And then what we get is we have negative 1/2 times du equals sine of 2x dx. Oh, I forgot to update the original function. So now we have to make some kind of a modification to what I call the skeleton. The skeleton is the thing that has the du and the u without the actual function values. It's just a general case. So now we have the sine of 2x dx. I'm going to replace all of that with negative 1/2 du. And then we have all of that over cosine of 2x, that is u. Oh, sorry, I meant to put the d in front of the u. That's supposed to be du, and then we have that over u. So now things are a bit more complicated. There's a few more extra steps we have to do in this one versus the one we last did. So I'm going to take this entire constant. I'm going to move it out front. So we're going to have negative 1/2. And then if we take the integral or the antiderivative of du over u, we get natural log of u. That would be natural log of cosine of 2x. So yeah, to answer your question, we can always just multiply a constant to the other side to make this match what we have on the other side. That only works with a constant though. If we had something like this, if we had, I don't know, maybe 2x, we can't just divide by an x. We can't divide by a variable because that affects not only our antiderivative, but the original function as well. So we can't just divide by x the same way we would with a constant. We can only divide by a constant. Does that make sense?
Yeah, just, got to practice this.
Yep. All right, let's see what's going on here. So let's see if we can find the exact solution. Up until now, we've been just finding general solutions that kind of just point to what we call a family of functions. We get an antiderivative of blah, blah, blah plus c, where c could be anything. C could be 1, c could be 2, c could be literally any number, and that's why we call it a family of functions. It's not just one function, it's a family. So we want to see if we can go from a general solution to a particular solution. Let's say we have something like this. We have e to the x plus, no, I don't like this one. Sorry, hang on a second. I really don't like this one that's in our book. All right. Let's say we have 12x squared plus 6x minus 4. And then we have this condition, f of 0 is 4. So I want you to start by taking the antiderivative of this. See if you can integrate this for us. Very nice. So what we're going to do is if we want to transition from having a family of functions to having one particular solution, we want to use this. We call this an IVP. This is an initial value problem. And the initial value is given by this. It tells us that whenever x is 0, y is 4. So we have all of this is equal to y. They give us a set value for y. They give us a set value for x. So I'm going to plug in everything for x, plug in 0 for everything for x. So this is going to become 0 and a 0 and a 0 plus c. equals y, which is 4. So that tells us that c, our constant c in this case, has to be 4. So in this case, we would just go back to the original, make a quick modification, replace the c with the value that we just found. So this would be the particular solution right here. That's what we call an IVP, an initial value problem. Any questions?
Nope.
Cool. Now, I was hoping we could talk a bit about the physics applications of derivatives and antiderivatives. Are you familiar with the calculus relationships between acceleration and velocity and position?
I've heard of them and I've done problems with them, but in terms of the integral or derivative definition, probably not.
So we know that the velocity is a rate of change in position. So the velocity is always going to be the derivative of the position. And then acceleration is the rate of change of velocity. So acceleration will always be the derivative of velocity. And the inverse relations apply as well. So velocity is going to be the antiderivative of acceleration, and then position is going to be the antiderivative of velocity. So let's try a sample problem.
Could we write all that down first?
Oh, yeah, sure.
Okay.
Give me a quick second. So these are the main ones we're going to be using in this class.
Okay. So x of t is position. Okay. Yeah.
All right, let me know when you have it all down.
All right, I've got it.
All right, let's try an example. All right, so we have this information. Our goal is to find the position function. We want to find x of t. What would be the first thing we want to do in this situation?
Use our information to find v of t.
Good call. How would that work?
We have I think we have to use those like the derivative properties of these three functions as well to change a of t somehow.
Yeah, we have an acceleration. How do we go from acceleration to velocity?
Take the derivative of one of them. I don't know which.
So so if we're going backwards, we're going from acceleration to velocity. Do we want to take the derivative or the antiderivative?
I think the antiderivative.
Yep, exactly. We have to take the antiderivative of the acceleration function to get the velocity function. So
So
see if
the
you can find that
derivative,
for us.
so the derivative of the velocity is acceleration, basically.
Yes. And
Okay.
the antiderivative of acceleration is velocity.
Okay. So, well, V of t would become, or no, antiderivative. So the velocity function with respect to time would be 3t squared plus 4t. And then,
Exactly. Plus c.
what do you mean?
Remember, we always have to have plus c when we take an antiderivative.
Oh, yeah, that's right. Plus c. I
So
didn't think
if
that
you
was
don't
going to
mind,
apply here.
could you write that on the board? Could you write
Yeah,
the
sorry.
velocity function?
Okay.
Very nice. So is it possible to find c at this point?
I think so.
It absolutely is.
We have, oh, this is like a IVP.
This is,
Okay.
yep, this is an IVP, exactly.
So, okay, so C is -6, so I will undo that.
Excellent.
Give me one second, I'm just writing all this down as we go.
No problem. Take your time.
Okay. So now I'm assuming we have to use a relationship between VT and AT that gets us XT, but I don't know what that relationship might be if such a relationship exists.
Well, we went from AT to VT. Now we want to do one more step. We want to go from VT to X of T, where V is the velocity, X is the position. So we can tell from the kinematics above that the position is the derivative. No, sorry, velocity is the derivative of position. So if we want to go backwards, what do we have to do then?
We would have to take the second antiderivative
Bingo.
of AT or just the antiderivative of VT.
Exactly. So go ahead and find that for us. Find the antiderivative of V of T.
Okay. So X of T, I'm assuming is going to be
Almost there. One more thing we have to add on that.
plus C. Dang.
Yep. And we
And
have
then we
yet
have to
another
solve
IV.
for C.
Yep.
Yep. Oh, this is almost always going to be what uh, when it's when you have that when you have the x is 0 or t is 0 and then it's equal to something. C is pretty much always going to be that.
Yep. In this situation, yeah. There are going to be some cases where it doesn't really work out that nicely, though.
All right.
All right, there you go. That is our function, our position function. Very nice. Any questions about anything so far?
Nope.
Great. So let's go back to the definite integral. So remind me, what is the difference between a definite integral and an indefinite integral?
The definite integral has limits of integration. And when you solve for antiderivatives, you don't need C. Indefinite integrals don't have limits of integration, so you always add a C at the end of the antiderivative.
Perfect. So what information does a definite integral give us that an indefinite does not?
That is that. The range of the antiderivative,
A little more
or no,
specific.
the area. It'll give
Yeah,
us the area of the integral,
the area under the curve. Perfect.
area under the curve. Yeah.
I want to see if you can find the area under the curve bounded by this function right here.
I plan on it.
But I want to make this maybe a 2x. All right, give this a try. See if you can find the antiderivative, and then use that antiderivative to find the area under the curve from x is 0 until x is 1.
Could I do the thing where you move the 2x out of the integral, or should I just calculate the antiderivative first?
You can only move a constant out front. You can move the 2 out, but you can't move the x out front.
Could I move the 2 out before calculating the antiderivative?
Yeah, definitely. You can always do that with any constant.
Okay. Oh, also, would I be using the use substitution here?
Yes.
Okay. You might want to pause the recording then.
All right. Thank you for the heads up.
Yeah.
Going on pause. Yeah, all right. So let's talk about the relationship between u and d. We know one has to be the derivative of the other. So we want to see if we can identify something that looks like the derivative of something else. Do you see anything that might fit that description?
Nope. I tried.
So a good strategy in a situation like this is to see if there's kind of like an outer function and an inner function situation, kind of like what we did with the chain rule when we're learning derivatives. So do you see anything that could be a clear outer and a clear inner function?
I would say that x could be the outer and square root 1 minus x squared could be the inner.
I was thinking that the inner could be the radical, or sorry, the outer could be the radical, and then the inner could be everything that appears under the radical. So let's go ahead and
Oh,
try that. So let's see if we can make this u equals 1 minus x squared. And then I want to see if you can take it from here.
I'll definitely try. Um, Wait, how'd you get square root of 4?
Oh, sorry. That's just because my handwriting is so horrible. That's supposed to be u square root.
Oh, my bad.
Yeah, my handwriting is really bad.
No,
So
I think
I
I
apologize for that.
can't tell for anybody's handwriting really. But how did we go from the top to the bottom? Because so we identified u and then du, but so where does the 2x go? Because I have and it's because I would have 2x and then du dx or no, just du over u.
So I want to do some rearranging real quick. So what we're going to do is I'm going to move the radical to the front, and then I'm going to move the 2x close to the dx. Just changes the way it looks without changing the value. It's still going to be the same answer. So the whole reason for doing that is because I'm going to combine these two, and
Mhm.
I'm going to go over to the differential equation. Du is negative 2x dx. I'm going to multiply both sides by -1. So the du becomes negative, and the other side becomes positive.
Yeah.
So then
Oh,
from
so do
there,
we replace that with negative du then? 2x
exactly. So I'm going
dx?
to replace everything in the box with a negative du. And then I'm going to replace everything under the radical with u. So this is going to just become a square root of u. But what I want to do is instead of having the negative sign right there, I'm going to move the negative sign to the outside of the integral. And I didn't give myself enough room for that. So the negative from the du goes out front, and we have square root of u.
Oh, I see.
So see if you can take it from here.
Would this be where I substitute in our values for u and du
Well,
to find the,
we want to integrate first and then substitute.
okay. How exactly would we go about finding the antiderivative.
So let's think about if we were finding the derivative. We have square root of u. That can be written as u to the 1/2. How do we find the derivative of u to the 1, or anything to the 1/2 power?
Power rule.
Exactly. So we want to change this into u to the 1/2 power, and then we want to use not the derivative power rule, but the antiderivative power rule to help us with this.
What's the antiderivative power rule?
So for derivatives, we know we have to multiply it by the constant and then subtract the exponent by 1. So for the antiderivative version, we're going to do the exact opposite. We're going to add 1 to the power and then divide by that result. So what do we get when we add 1 to our exponent?
3/2.
Exactly. And then we're going to divide by 3/2, which is the same as multiplying by 2/3. Going from
okay.
0 to 1. So our very next step is to put u back in there and then evaluate.
Wait, what about du?
Well, whenever we integrate, the du goes away and the integral sign also goes away. So we just integrated, we only have u left.
Oh, okay. Why does it go away? Is that happens every single time?
Yeah,
Always?
because, yeah, exactly. Whenever you integrate, we don't have any more calculus to do. This is part of the integration process. This is also part of the integration process. When you take the integral of something, both of those things go away and we're left with only algebra. The only thing to do is just to substitute in our values. We're completely finished with the calculus part of this.
Okay. So this is where I would solve for area, right?
Yes.
All right.
All right, you got 2/3 for the area.
Mm-hmm.
Very nice. Nice work. So let's try a slightly different function. So I'm going to remove the 2x. And I want to see if you can integrate this, see if it's possible using all of the tools we've learned so far.
Okay. Well,
And, could you write that on the screen, what that would look like? Yeah, thank
yeah.
you.
Give me 1 second. Okay, sorry, I'm back. That's what that would look like, but I'm not sure how it would help me.
Yep. So I'm a really horrible person. I gave you this problem knowing that we don't have enough tools in this class, knowing that we haven't learned the tools yet to integrate this, but I wanted to try it out. I was curious to see what ideas you might have. So we can't integrate this, but we can find an answer without integrating. Can you think of an idea of how we could possibly get this answer without doing a lick of calculus?
Doing the antiderivative power rule and then just solving.
Well, that would involve calculus. There's a way to get this answer without doing a single derivative, a single integral, a single limit. There's a way to get the answer without a single lick of calculus.
The only thing I could think of would be just doing it with the square root 1 minus x squared. You know, substituting 1 and 0 in for that, but
Well, that wouldn't really work because we can only plug in limits of integration to get an area when we have an antiderivative. So I want to go ahead and graph the function. This is, remember, this is just what we get when we try to graph a circle with a radius of 1. This is y equals square root of 1 minus x squared. The general case would be r squared minus x squared, where r would be the radius. In this case, r squared is 1, so we have a radius of 1. It would look, hang on, let me draw it here. So this is what it would look like, except we don't have the bottom half. So this is our function. And remind me, what do integrals tell us about a function? What does a definite integral tell us about a function?
it tells us the area of something.
Yeah, area under the curve. In this case,
Area under the curve.
we're going from 0 to 1. So it would look like that. So now what we want to do is we want to assign a value to this. So we know that it's going to be a quarter of a circle with a radius of 1. So the circle is going to be pi r squared. This is going to be pi over 4 for our area. We didn't have to do a single derivative or a single antiderivative to get our answer. We just had to use some geometry knowledge. And we had to use the fact that we know that an integral gives us the area under a curve on a particular interval. Mind
Oh,
blown.
wow. Yeah.
There is a way to integrate this, but it's not going to be anything we learn in this class. You might be thinking, how do we get such a weird value? How do we get something involving pi for something like this where we have nothing with sine? Nothing
Yeah,
with sine?
actually.
How do we get something
Huh.
with pi if we're not integrating a trig expression? So the way we integrate something like this would be using inverse trig relationships. We would probably say this is equal. We'd probably use some kind of a substitution. We would say x is sine of x. No, sine of theta, not x.
But how could you just do that? Wouldn't that couldn't that change the whole meaning of the expression?
Well, only if dx and x mirror the same thing. So if you change x without changing dx, you can't just arbitrarily change things like that. But if you modify dx, you can. It's kind of like if you have something like this and you want to find a common denominator. You can't just arbitrarily multiply the top by x without affecting the value. You also have to multiply the bottom by x, and then it affects the whole thing. And that way, it's legal to do it that way. And with integrals, it's the same way. As long as you modify one thing, you have to modify everything else. Otherwise, it won't be the same anymore. So if x is sine of theta, dx is going to be cosine of theta d theta. And then x squared is going to be sine squared theta. So this is going to be 1 minus sine squared theta under the radical. And then you can simplify that. You can use the Pythagorean identity. 1 minus sine squared theta is equal to cosine squared theta. And then remove the radical and you get just cosine of theta. But things are a bit more complicated than that because we still have cosine of theta out front from the dx. And originally, I was thinking we weren't really going to get that much into the trig substitution, but you are getting through this stuff much, much faster than my other classes have in the past. So we could very well have enough time to do all of this stuff as well.
Okay. Wow.
Yeah, like you're learning this stuff at an extremely quick pace, like much faster than the other 3 times I've taught this class.
I'm trying.
You're doing great. So let's see. So I was thinking that we could talk a bit about the fundamental theorems of calculus. There are 2 of them. I know we talked about them briefly, maybe last class or maybe a few class sessions ago. Do you remember what they are, or in just a general sense of what they do?
No.
All right, no problem. So we're going to talk about the first part of the fundamental theorem of calculus. There are 2 parts. The first part tells us this. It tells us that if f is a continuous function, here I think I'll just type this part as well. So I highly recommend you put this in your notes. The 2 fundamental theorems of calculus are really, really important.
I'm gonna need to get a piece of paper. Give me a second.
No problem.
Is that a and x, are those the limits of integration?
Yep.
Okay.
All right, let me know when you have this.
I have it.
All right, cool. First part of the fundamental theorem. So what is your interpretation of this? So we have g of x defined as some kind of integral, and then we have g prime of x defined as some other function. And notice how they're both given the identifier f, but the variable of integration changes. This has a variable of integration of t, and then this one down here has a variable of integration of x. So what is your interpretation of this? What do you think this all means?
I think that g is like the antiderivative of f of x.
Yeah. Well, the derivative.
And
So we can see that the g of x is the derivative. We have g prime of x is f of x. So g of x is the derivative of f of x.
what do you mean g of x is the derivative of f of x?
Oh,
The
wait.
g of x is the derivative of f of x. So when you take the derivative of g of x, wouldn't that make g of x the antiderivative of f of x?
Yes.
Yeah. Okay. So I think that g of x, since we know it's an integral and it has these limits of integration, I th I think that it represents like a certain portion of f of x, where f of x represents a certain portion or like area under g of x. That's my best guess, though.
Well, it's interesting how instead of having two constants, like for example, we're used to having a and b as the limits of integration, we have a and a variable. So this is the thing that really establishes the relationship between derivatives and integrals. This is the thing that really tells us that derivatives and integrals are opposites of each other. So if we take this definition of g of x, and we take the derivative of both sides. So if we take the derivative of g of x, we get g prime of x. If we take the derivative of an integral, the integral just goes away. We know that they cancel each other out in the same way that multiplication and division cancel each other out. So we no longer have an integral situation. We just have a function. But then what happens is we change the variable of integration. Right now it is t, but after we integrate, that changes the variable of integration to x. So instead of f of t, we now have f of x. And that's really all it does. That's really just the gist of the first fundamental theorem of calculus. It rigorously establishes the fact that they are opposites of each other, that derivatives and integrals are inverses of one another.
Oh, I see. Okay.
So it would work. Let's try an example. Let's try this. So let's say we have the integral going from 0 to x, and this is g of x. G of x is defined as the integral going from 0 to x of 1 plus x squared. Dx. Can you find the derivative of this for me? Can you find g prime of x?
So first I would calculate the antiderivative, right?
Mhm.
And then I would just find the derivative of that.
Yes.
But for the limits of integration, would I have to do anything with those?
Nope. Because we're keeping the same variable of integration. In this definition, we used x and we used t, but in this one, we're keeping the variable of integration x throughout the entire problem.
Okay. Could I apply the antiderivative power rule to find the antiderivative of this?
Well, we're not trying to find the antiderivative. We're trying to find the derivative. We're trying to find g prime of x.
So how do you find the derivative of an integral? Do you just take the derivative of what's in the integral?
Nope. Remember what the fundamental theorem of calculus tells us. It tells us that derivatives and integrals are opposites. It tells us that if we take g prime of x, in this case, the integral goes away and we're left only with f of t, or in this case, f of x when we have the change of variable. So whenever we take the integral of a derivative, they both go away. Whenever we take the derivative of an integral, they both go away. So to find g prime,
Oh, are they like reciprocals almost?
they're more,
Eh,
reciprocal isn't really the right word. They're inverses.
Inverses, yeah, that's a better word. And
It's kind
then
of like how you take, if you have something like this and you want to solve for x, we have to take the natural log of
yeah, of
both
both
sides.
sides, and then it cancels out the e.
Exactly. Derivatives and integrals work the same exact way. So see if you can find for us g prime of x based on this definition we have for g of x.
So wouldn't it just be plus a square root of 1 plus x squared?
Yep, that's it. That's g prime of x.
Okay.
So now let's
Make a
try
note.
a slightly different one. Same fundamental theorem, but different problem. I want to see if you can find for us the derivative with respect to x of the integral going from 1 to x to the fourth power of secant of t dt. And this one is pretty similar to the last one, but there's an extra step. We actually have to use the chain rule in this one because we have an upper limit of integration being substituted in for t. So when we take the derivative of an integral, they both go away, but then remember that we changed the variable of integration. So instead of having secant in terms of t, we're going to have secant in terms of x. We're going to substitute the limit of integration in for t. So that would become secant of x to the fourth power, but then we also have to apply the chain rule. Last time we didn't have to do that because we just had x and the derivative of x is just 1. This time we do have to make sure we have that part factored into the expression. So we have the derivative of x to the fourth power gets us 4x cubed. So our integral, this will turn into secant of x to the fourth power times the derivative of this, which is just going to be 4x cubed. And that's it. So this would be our answer. Secant of x to the fourth power times 4x cubed. That is the derivative of this integral.
So about this, so whenever we like cancel out an integral with a derivative that an integral has limits of integration, or the b limit is another variable, we have to swap them out, or is it just because of how we see in the theorem, g of x is equal to f of x. So if, I mean, g prime of x is equal to f of x. So if g of x has t as the main variable, you just have to swap it.
Yep, you always swap whatever the upper limit of integration is after you cancel the integral and the derivative out. This thing in the box right here instantly becomes your new variable of integration, or in this case, a new argument of integration. X to the fourth power would be the argument of integration.
And why does the extra step come here of chain rule?
Because whenever we're taking the derivative of something, we have to take the derivative of any time we have an inner function. So last time we didn't have to do that because we just had x and the derivative of x is 1. But this time we have something other than just x. So we have to apply the chain rule whenever we take the derivative of anything. In this case is no exception.
When you say last time we just had x, what do you mean by that?
So remember in the last example we did, we had just x as the upper limit of integration, you remember?
Yeah.
It wasn't x to the fourth power, it was just x. And the reason why we didn't have to do the chain rule in the last step is because the derivative of x is just 1.
So the last one, inside of our integral, we had square root of x squared. So, but then g prime of x, we said it was equal to square root of 1 plus x squared. So where did we only have x then?
Here, let's see if we can go back. Here we go. So we took the antiderivative of this. We got 1 plus x, we got the square root of 1 plus x squared. The derivative and the integral canceled each other out, but notice what is our upper limit of integration here?
It's x.
It is x. And then what is the derivative of x?
1.
Exactly. So we did do the chain rule in this one, but it just ended up being invisible because
Oh, so when you swap the variable, or even if you don't, because your result has the variable, you still have to take the derivative of the upper integration limit.
yep, always.
Oh, okay.
This one, it didn't have any effect because the derivative of x is 1, but in this one, it does make a difference because we have an argument of integration of something that's other than just x. In this case, it was x to the fourth.
Okay.
So that is the first part of the fundamental theorem. Any questions?
No. So far, so
Alrighty.
good.
Let's get into the second part. Second of two parts. This is the one we've already had quite a bit of exposure to, but I still feel like it's a good idea to rigorously define it, just to make sure we have a complete understanding of how it works. So we have this, and then we have one more part that goes on the bottom, where capital F of x is any antiderivative of lowercase f. That is a function such that capital F prime is equal to lowercase f. All right, and we've already had quite a bit of experience with this one. This is the thing that explains to us that how we find the area under a curve, how we use the definite integral to find the area under the curve. So capital F is the antiderivative. So all we need to do is we need to find the antiderivative of lowercase f of x, and then we need to plug in b, and then subtract the same exact function, but this time we're going to plug in the argument of a. So this is just the thing that rigorously defines the area under the curve as the antiderivative of the top minus the antiderivative of the bottom.
Mm-hmm.
So I know we've done this quite a bit, but let's practice a bit more.
So capital F is pretty much the antiderivative for the quote unquote original function.
Yes.
Okay.
I want to see if you can find for me the area under the curve from 6 to 3 of the function 1 of dx over x.
Do you want an exact answer, or can I just leave it as a function and an argument?
So what did you get for your answer?
I got the area to be natural log of 2.
All right, perfect. Yeah, that works very well.
Okay.
Very nice. So let's try another example of this. So I want you to find the area under the curve of this expression. On the interval 0 to 4 pi. Give it a shot.
Okay.
Actually, hang on. Let's make it. Hang on just a second. I think I had a different function in mind for this. Give me a quick second.
Okay.
All right, I wanted this actually to be cosine. So let's have it be cosine of x over 2, or 1/2 x, same thing. And then let's integrate from 0 to 2 pi. There you go. We're good to go now. Bounded by this expression on this interval. And I think I'll pause the recording while you work on this. Sorry, what was that?
Is the area 0?
Interesting. So the math would make it look like it is, right? But clearly, if we look at the graph, and this is a very poor drawing, I know, but the graph kind of looks something like this. So how could the area be 0?
Well, if I remember from last time we talked about this, this part right here is like it's like it's not a negative area, but it is at the same time, I think.
Yeah,
So, and I think
exactly.
that these two are equal to each other. So they sort of just like cancel each other out, or when you add them both, they amount to 0.
Perfect. Exactly right. I'm glad you remembered that. So if they asked us to find the integral, 0 would be the correct answer. But if they asked us to find the area bounded by this expression, we get 0. That would be incorrect because the area actually isn't 0, even if the integral itself is. The area is different than just the integral. So I want
Wait,
to see if you
so
can find the area bounded. And we want to make sure, do you remember how to accomplish that?
uh I just have a quick question. So you said that there was if it asked us find the area bounded by, the answer wouldn't be 0. But what was the question you said the answer would be 0?
So if they just asked us to find the integral of this expression right here,
Uh
0 would be a perfectly acceptable answer for the integral, but for the area, we're going to need something other than 0 because we can see that 0 isn't the true area. How do we find the area, though? How do we find the true area? Going off on the fact that this kind of accounts for what can be described as a negative area, and the fact
I
that
would
they are equal
say,
to each other.
well, pi is equal to 180 degrees. 2 pi is 360. So what I would say is we change the range to just pi, calculate the positive area, uh for a lack of better words, and then just multiply that by 2.
You mean the domain, right?
What do you uh e
Change the domain from 0 to pi, right?
yeah, change the yeah, did I say range?
Mhm.
Okay, yeah, sorry, I meant domain because it's hard. Yeah, so I would change the domain to 0, from 0 to pi, from 0 to 2 pi to 0 to just pi,
All
and
right,
then
that makes sense.
calculate.
Let's modify this just a little bit. Instead of going from 0 to 2 pi, let's go from 0 to 11 pi over 6. I want you to find for me the area bounded by this expression.
Okay.
Area bounded by the graph of this expression is what I meant to say.
I created a ratio where so we have pi over 2 is equal to 5 pi over 6 over x. And basically it's just like um it's like a relationship that says when the domain goes all the way to pi, the area is 2. So I use that to just try to find the area when the domain goes to only 5 pi over 6. And then
Wow.
this comes out to be 5 over 3. but that's only for 0 to 5 pi over 6. So instead, what I did was I just added 2 plus 5 over 3 to get the total area, which I put over as I turned it into a fraction total and came out to be 11 over 3.
That's really impressive. I didn't even think to do it that way. But let's see if it is accurate to the actual answer. So another way we could approach this is to build on what you have right here. It's a good idea to break it up into multiple integrals. You can always do that. Instead of going from 0 to, this would be 11 pi over 6 of anything, any expression really. Generalize it, g of x. You can break it up into as many sub-integrals as you like. For example, you could do something like this, integral blah, 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 plus integral going from pi to 11 pi over 6. This is perfectly legal. You can always break up an integral into as many sub-integrals as you like. So
Would you want to do it though from pi to 11 pi over 6?
Well, in this case, we want to identify the region where it has a negative area. So every time we go from 0 to pi, that would be positive. Every time we go from pi to 11 pi over 6, this would have to be negative. So what I want to do is I want to take the absolute value of, or maybe not the absolute value. I want to make this negative because then we'll have a negative negative and we'll make it positive. So I agree with what you've done, 0 to pi. For part, I'm going to call this part A. For part B, what I'm going to do is I'm going to take negative integral because we know it's negative. I'm going to put a negative in front to make it positive, and then our limits are going to be pi to 11 pi over 6. Same function. So then we get 2 times sine of 1/2 x.
So you put the negative out in front because
yeah, I forgot that. Thank you.
Because the negative, it's the area where the altitude is negative basically.
Exactly. So I have -2 out front. If I got rid of the negative, this is a negative area, but I want to put the 2 back out there to make it positive because we know we can anticipate when a region is going to produce a negative area. We always multiply by a -1 to counteract that, to make this a positive area instead of a negative area.
To just find the total area.
Exactly. So we find the total area of part B, and then we add it to your answer you have for part A. And that's all the time we have for now. It's good for us to take a break, and I'll see you in an hour from now. Any questions before you go?
Was I right? Or I mean, was my method for part B basically, was that okay?
Actually, what can we verify that when you come back in about an hour?
Yeah.
All right. We'll see you in an hour then.
Okay. See you in an hour.